Hello again, 1CHEA, B, and C. You are now watching Lecture 4B entitled Acid-Base Equilibria. At the end of this discussion, everyone should first know the different principles of acid-base equilibria. Next, learn how to calculate the pH of different types of solutions. Next is explain the principles of buffer solutions and learn how to calculate buffer-associated problems. And then lastly, you should be able to explain the common ion effect in acid-base equilibrium. So now, let us start with the principles of acid-base equilibria. How do we know if a substance is an acid or a base? In this lecture, three different definitions will be introduced. Let's start with the Arrhenius definition. An Arrhenius acid is a substance that contains hydrogen and yields a hydronium ion when placed in water. An example is hydrochloric acid, HCl. When reacted with water, it produces hydronium H3O plus and chloride Cl minus ions. Similarly, it can be presented as HCl yielding hydrogen H plus ions and chloride ions. Pag nakalagay yung water sa reaction, hydronium ions ang mafo-form. Kapag wala ang water, hydrogen ions naman ang mafo-form. Either way, pwedeng gamitin. Naka-shortcut or mas madali lang isulat pag wala na si H2O. On the other hand, Arrhenius base is defined as a substance that contains hydroxyl OH- group and produces hydroxide OH- ions when placed in water. An example is dissociation of sodium hydroxide in water to yield Na plus and OH- ions. If the hydronium ion from the acid reacts with the hydroxide ions from the base, the process is called neutralization. The reaction is shown below. Here, it can be observed that water is produced and the process is exothermic because of the negative delta H value. Pag naghalo ka pala ng acid and base, mararamdaman mong umiinit yung reaction. Next, we have the Lewis definition. According to Lewis, an acid is a substance that accepts an electron pair, while a base, on the other hand, donates an electron pair. Yung binibigay ni Lewis base is yung tatanggapin ni Lewis acid. The result of any Lewis-base reaction is called an adduct. It is short for addition product. So bakit siya tinawag na addition product? We can see from the reaction that the product is simply the addition of Lewis acid and base chemical formula. Pinagsama lang talaga natin yung dalawa. An example is the reaction of nickel ion with 6 moles of water to produce a nickel complex, NiH2O6 2 positive. The nickel ion accepts the electron pair donated by water molecules to form the adduct, the nickel complex. To have a practice on identifying Lewis acids and bases, let's try the following reactions. You may pause the video if you want to try it first on your own. The answers to the problem are as follows. The Lewis acids are colored red, while the Lewis bases are colored sky blue. Again, si Lewis acid ang nag-a-accept ng electron pair donated by the Lewis bases. Kung mapapansin ninyo, Lewis acids usually ang may mas mataas or mas positive na charge sa kanila. Lastly, we have the Bronsted-Lowry definition. Here, an acid is described as a proton donor, or any species that donates a hydrogen ion, thus it must contain H in its formula. Examples are nitric and hydrochloric acids. Based from this definition, we can conclude that all Arrhenius acids are also Bronsted-Lowry acids, and also vice versa. On the other hand, a base is defined as a proton acceptor or any species that accepts a hydrogen ion. For it to accept the hydrogen ions, it must contain a lone pair of electrons. Examples are ammonia, carbonates, fluorides, and hydroxide ions. From these definitions, we can conclude that all Arrhenius bases are Bronsted-Lowry bases dahil nga sa hydroxyl group. However, not all Bronsted-Lowry bases are Arrhenius bases because there are other bases outside the hydroxyl group. As mentioned earlier, ammonia, carbonates, and fluorides are also counted as base according to the Bronsted-Lowry definition. From now on, Remember these definitions of Bronsted-Lowry as the succeeding slides will be based on these definitions of acids and bases. Now let's introduce the concept of conjugate pairs. It is shown that for an acid-base reaction, the products will have a conjugate base and a corresponding conjugate acid. The conjugate base is the substance formed after an acid donated a proton or hydrogen ion. By contrast, the conjugate acid is formed after a base accepted the proton or hydrogen ion donated by the acid. The acid and its corresponding conjugate base are considered conjugate pairs. Similarly, the base and its corresponding conjugate acid are also conjugate pairs. To better understand the conjugate pairs, let's look at the following reactions. Reactions 1 to 6 show different acid-base reactions and their corresponding conjugate pairs. The first column shows all the acids from the reaction. The corresponding conjugate bases are shown in the third column. The highlighted columns are conjugate pairs. Next, we have the bases in the second column, while their corresponding conjugate acids are shown in the last column. Again, they are also called conjugate pairs. Take note that the conjugate pairs must have almost the same chemical formula. The only difference is the inclusion or exclusion of the hydrogen atom or ion. Let's now have some practice in identifying the conjugate acid-base pairs. If you want to try answering on your own, you may pause the video. The highlighted substances show the correct acid and conjugate base pairs. Again, kailangan same ang chemical formula nila. May sobrang H lang yung acid sa chemical formula compared sa conjugate base pair niya. The next highlighted substances show the correct base and conjugate acid pairs. This time, yung base naman ay kulang lang ng H sa chemical formula when compared sa kanyang conjugate acid. Next, let's introduce the concept of amphiprotic species. When we say amphiprotic, it means that an acid or that it can either act as an acid or base. Using the Bronsted-Lowry definition, it can donate or accept a proton. Considering water as an example, in this reaction, water is considered as an acid as it donates a proton or a hydrogen ion. On the other hand, in the next reaction, it can be seen that water accepts hydrogen ion. Thus, it is considered a base. Because water can act either as an acid or base, water is considered amphiprotic. Amphiprotic solvents undergo self-ionization to form a pair of ionic species. The process is also known autoprotolysis. Meaning, kaya nila mag-dissociate into ions on their own. The autoprotolysis of water is shown as an example. Makikita natin na kayang mag-dissociate ng water into hydronium and hydroxyl ions without the presence of other substances. To have a clearer picture of autoprotolysis, let's consider the following reactions. It is shown from these reactions that self-ionizing substances, or those that undergo autoprotolysis, do not need the presence of other substances to disintegrate into ions. Makikita natin sa reactant side na sa sarili lang nila sila nakikipag-react. Focusing again on water, it is known from experiments that the hydronium ion, H3O+, and the hydroxide ion, OH-, concentrations at 25 degrees Celsius are only about 10 to the negative 7 molar. Kung iisipin, sobrang konti lang din talaga ng mga ions na na-form. Hindi talaga lahat nagdi-dissociate to ions. Kakaunti lang din talaga. But how was this value obtained? Recalling the reaction of water, the equilibrium constant can be written as the ratio of the concentration of the products over the reactants as discussed in the previous lecture video. The ion product for water was denoted by Kw. Based on literature, it is equal to 1 times 10 to the negative 14 molar at 25 degrees Celsius. Applying this value to the formula above, it can be computed that the hydronium ion and hydroxide ion concentrations at 25 degrees Celsius are only about 1 times 10 to the negative 7 molar. To better represent the values of hydronium and hydroxide ion concentrations in the solution, we will introduce the concept of pH and pOH. pH is defined mathematically as the negative log of hydrogen or hydronium ion concentrations. Again, parehas lang yung hydrogen and hydronium ion. Similarly, pOH is defined as the negative log of hydroxide ion concentrations. Recalling the hydronium and hydroxide ion concentrations of water and applying the formula for pH and pOH, it can be seen that the pH and pOH of water at 25 degrees Celsius is equal to 7. And it can be seen that the sum of this pH and pOH values is equal to 14. This realization is very important for our succeeding calculations in pH of various solutions. So what does this pH value tell us? It tells us how acidic or basic a solution is. Low values correspond to more acidic solutions, while high values correspond to more basic solutions. To better understand the relationship between pH and pOH, let's look at this diagram. It can be noted that as the hydrogen ion concentration rises, the hydroxide concentration decreases. Thus, it can be deduced that as the pH falls, pOH rises. Remember the relationship pH plus pOH is equal to 14. But how do we compute the pH and pOH of different acid-base solutions? Let's start by studying strong acid equilibria. You should take note that one property of strong acids is that they completely dissociate in water. Meaning, lahat naghihiwalay, walang natitirang magkasama pagka-reach ng equilibrium. So si HA ay totally magiging hydrogen and A- ions kapag na-reach na ang equilibrium. The equilibrium concentration of H plus is equal to the initial concentration of the strong acid, thus resulting to almost zero concentration of the acid in equilibrium. The equilibrium constant can be represented by the following expression. The ratio is very much greater than 1 because the numerator is too big compared to the denominator. An example of strong acid is the nitric acid. For strong base equilibria, everything is almost the same with strong acid. The only difference is that it produces hydroxide ions instead of hydrogen ions as highlighted in the reactions. Similar to strong acids, a strong base also completely dissociates into ions in water. An example of strong base is the sodium hydroxide ions or sodium hydroxide. So how do we calculate the pH of strong acids and bases? First, let's recall the formula for pH. For strong acids, the hydronium or hydrogen ion concentration is equal to the initial concentration of the acid because sabi nga natin kanina, they completely dissociate in water. So to calculate pH, we just need to plug in the concentration of the hydrogen ion and then we can solve for the pH. Mabilis lang talaga ang calculations kapag strong. On the other hand, for the strong base, the hydroxide ion concentration is equal to the initial base concentration. Again, dahil nga sa nagde-dissociate rin siya completely. After getting the OH minus concentration, we can compute for the H plus concentration by plugging into the following relationship. Ito yung na-discuss natin kanina sa autoprotolysis of water. After solving for the H plus concentration, we can now plug in sa formula for pH. For strong base, we have another option for solving the pH. Pwede rin na after masolve ang OH minus concentration, we can solve for the pOH using the following formula. Then after solving for the pOH, we can use the relationship to solve for the pH. Again, ito yung na-discuss din natin kanina sa autoprotolysis of water. Sample problems will be discussed later to better understand these steps for pH of strong acids and bases. Now that we understand strong acids and bases, how do they differ from their weak counterparts? From this figure, it can be observed that the upper half diagrams pertain to a strong acid. It is because of the complete dissociation at equilibrium. On the other hand, the bottom half diagrams pertain to a weak acid. It can be observed that from the diagrams that weak acids or bases do not dissociate completely at equilibrium. Sobrang konti nga lang nang nagdi-dissociate if pagbabasehan ang figure. So now, to further understand weak acids, let's discuss weak acid equilibria. As shown in the figure earlier, weak acids dissociate very lightly in water. The reaction is still the same, but we can expect very minimal amount of H3O plus and A minus in the product. Thus resulting to much lower hydronium ion concentrations compared to acid concentration. The result would be an equilibrium constant value that is much less than 1 because the numerator is much lower than the denominator. So how do we solve for the hydrogen ion concentration if it is much lower than the acid concentration? The solution is the acid dissociation constant Ka. It is also the same equilibrium constant discussed earlier. The subscript A denotes that it is for acids. This constant is an empirically determined value to describe the dissociation of weak acids. It tells us that the larger its value, the stronger the acid is. Thus, more hydronium ions can be observed from equilibrium. As a summary, you can take a look at this schematic diagram. Because Ka values are usually very small and expressed in scientific notations, similar to pH, pKa values can also be used to better represent Ka values. pKa is defined as the negative log of Ka. Comparing the values of Ka and pKa for some acids, we can observe the trend that as the Ka value decreases, the pKa value increases. From here, we can deduce that since larger Ka values signify greater strength of acids, stronger acids tend to have low pKa values. In this set, we can say that hydrogen sulfate ion is the strongest among the weak acids on this list. For weak acid equilibria, again, the reaction is the same for strong base. We could expect less ions on the product side. Thus, the equilibrium constant value will be much less than 1 because of this. The Kb or dissociation constant value can also be used to calculate the hydroxide ion concentration. Kung kanina, binanggit natin na gagamitin ito kung kanina si Ka binanggit natin na gagamitin to compute for H plus concentration for weak acids, ngayon ay Kb naman ang pwedeng gamitin for weak bases. Similar to pKa, pwede rin natin makompute si pKb. Comparing the values of pKb and Kb, similar to Ka and pKa, it can be observed that they are inversely proportional. So to summarize the steps for computation of pH for weak acids and bases, let's recall again the formula of pH. It's negative log of H plus concentration. Then for weak acids, use the formula for Ka to relate the species involved. Use the ice table discussed in lecture 4A to compute for the concentration of the species. Then, apply the formula for pH. For weak base, use the formula of Kb to relate the species involved. Use the ice table to compute for the concentration of the species. Then, use the relationship to solve for the H plus concentration calculated from the calculated OH minus concentration. Then, apply the formula of pH. If you have observed, the steps are similar to the ones we discussed for strong acids and bases, except for the first part. Because weak acids and bases do not dissociate completely, mas mahaba ng kaunti ang process niya dahil kailangan pa muna natin ma-determine ang H plus and OH minus concentrations from Ka, Kb, and the ice table. Dahil nga similar sa kanina, we can again have another alternative in solving for pH of weak base. POH can be again solved from negative log of OH minus concentration and then pH can be solved using the following relationship, 14 minus POH. To better understand these steps, again, sample problems will be shown later. Let us try to look if there is a relationship between Ka and Kb for conjugate acid-base pairs. Take note, we are only talking about conjugate pairs here. If you can recall from our previous slides, conjugate pairs have almost the same chemical formula. Yung H lang ang pinagkaiba. Solving for Ka of the acid reaction, we will get the following expression. Solving for Kb of the base reaction, we will get the following expression. Multiplying the two expressions, we will get, and then canceling similar terms will yield the expression. The right side of the equation is the definition of the ion product of water, which is Kw. Thus, replacing them with Kw will yield the expression Ka times Kb is equal to Kw. Expressing in terms of pKa and pKb will result to the following relationship. pKa plus pKb is equal to 14. Again, this is at 25 degrees Celsius. In this figure, dissociation reactions and relative strengths of some common acids and their conjugate bases are shown. The previously discussed relations can be applied in any of the conjugate pairs shown in the list. We can also see from this list the trend that for relative strengths of the conjugate pairs, a strong acid will result to a weak conjugate base, while a weak acid will result to a strong conjugate base. Here are the most common strong acids. You might want to memorize them as when you see them in the problems, you would know that calculations will be easier because they are strong acids. Here are some of the common strong bases. The hydroxides of the group 1 alkali metals and group 2 alkaline earth metals usually are considered to be strong bases. Again, just like the strong acids, you will be more than happy to see them in your self-assessment problems or quiz. Here is a list of some of the weak acids. You can find them in different books together with their Ka values. Here is a list of some of the weak bases. Common examples are organic compound with a nitrogen atom. Again, you can find them in different books together with their corresponding Kb values. Let us now introduce another concept, the fraction of dissociation alpha. Some books may call it percent dissociation. It is defined as the fraction of the acid in the form of A minus for the weak acid and BH plus for weak base. Basically, inaalam lang natin kung gaano karami ang nag-dissociate. The formula for fraction of dissociation for acid and weak base is given by the following formula. The formal concentration indicates that the moles of the original chemical formula in solution without regard for the species that actually exist in the solution. Para mas sumimple, ito yung given molar concentration ng weak acid and base sa problem. Kung mapapansin, ay similar lang ang formula ng fraction of dissociation sa percent by mass. Ang pinagkaiba lang ay nakamultiply sa 100 and concentration ang units instead of mass. Finally, we will introduce the concept of polyprotic systems. Polyprotic acids contain more than one H plus ion as implied from the prefix poly. Diprotic, on the other hand, contains two acidic hydrogen atoms as implied by the prefix di. Lastly, triprotic acids have three acidic hydrogen atoms. The analysis of acid or bases becomes more complicated as the number of acidic hydrogen atom increases. Fortunately, for the succeeding discussions, specifically calculations, we will focus only our attention to monoprotic acids. Monoprotic acids are those which contain only one acidic hydrogen atom. Now, let's try to do calculations involving acid-base equilibria and buffers. Sample problem number 1. Calculating H3O plus concentration, pH, OH minus concentration, and POH. In this problem, concentrated hydrochloric acid is diluted to two different concentrations as shown, and we are asked to compute for the H3O plus concentration, pH, OH minus concentration, and POH of the two solutions at 25 degrees Celsius. First step is to list down all the necessary givens and unknowns. Here, I highlighted the necessary givens, and if you can observe, I highlighted hydrochloric acid to emphasize that it is a strong acid based on our previous discussions. As explained earlier, calculations will be a lot easier for strong acids and bases. The table shows the summary of the unknown values in the problem. If you want to try this on your own, you may pause the video. Let's recall the steps for strong acids. First is to determine the H plus concentration. Again, for strong acids, it is equal to the initial concentration of acid. Next is to apply the formula of pH. This can be done very quickly using your calculators. Next is to solve for the POH value using the expression POH is equal to 14 minus pH. And then lastly is to solve for the OH minus concentration from the calculated POH value. Now we have completely solved sample problem 1. Next, let's try sample problem 2, calculating pH of a weak acid. In this problem, we are asked to compute for the H3O plus concentration and pH of a 0.12 molar nitrous acid. Again, first step is to list down all the necessary givens and unknowns. Here, I highlighted the concentration of the weak acid, nitrous acid, and its corresponding Ka because we will need them later in our calculations. Let's recall the steps for weak acid. First is to write the expression for Ka. Next is to solve the unknown concentration of species from the ice table. And then lastly is to compute for the pH using the calculated hydrogen ion concentration. Now that we have enumerated the steps, let's create the ice table. Ice table was already introduced in the previous lecture. The initial, change, and equilibrium concentrations are summarized in the table. Writing the expression for Ka will give us substituting the values in the ice table will result to this equation is quadratic in nature and contains only one unknown. Solving for the values of x will be easier if you know how to do quadratic equations using your calculators. Solving for x will give us 8.88 times 10 to the negative 3 molar. Based on the ice table, this is also the hydrogen ion concentration. Substituting this to the formula for pH will give us 2.05. Now, we have completely solved sample problem 2. Next, let's move on to sample problem 3. Similar to sample problem 2, sample problem 3 is also about calculating pH of a weak acid. In this problem, we are asked to compute for the H3O plus concentration and pH of a 2.0 times 10 to the negative 4 molar aniline hydrochloride. First step is to list down all the necessary givens and unknown. Again, I highlighted the concentration of the weak acid and its corresponding Ka because we will need them later in our calculations. Let's recall again the steps for weak acids. First is to write the expression for Ka. Next is to solve for the unknown concentration of species from the ice table. And then lastly is to compute for the pH using the calculated hydrogen ion concentration. Now that we have enumerated again the steps, let's create the ice table. Again, the initial, change, and equilibrium concentrations are summarized in this table. Writing the expression for Ka will give us, substituting the values in the ice table will also result to, the equation again is quadratic in nature and contains only one unknown. Solving for the values of x will be easier again if you know how to do quadratic equations using your calculators. Solving for x will give us the value 5.94 times 10 to the negative 5 molar. Based on the ice table, this is also the hydrogen ion concentration. Substituting this to the formula for pH will give us a pH value equal to 4.23. Now, we have completely solved sample problem number 3. Moving on to sample problem number 4, calculating OH minus concentration of a weak base. In this problem, we are asked to compute for the hydroxide ion concentration in a 0.0750 molar ammonia solution. First step is to list down all the necessary givens and unknowns. Here, again, I highlighted the concentration of the weak base ammonia and its corresponding Kb because we will need them later in our calculations. Let's recall again the steps for weak base. First is to write the expression for Kb. Next is to solve for the unknown concentration of species from the ice table. Now that we have enumerated the steps, let's create the ice table. Again, the initial, change, and equilibrium concentrations are summarized in the table. Writing the expression for Kb will give us, substituting the values in the ice table will result to, the equation again is quadratic in nature and contains only one unknown. Again, paulit-ulit tayo. Solving for the values of x will be easier if you know how to do quadratic equations in your calculators. Solving for x, we can get the value 1.14 times 10 to the negative 3 molar. We have now completely solved sample problem number 4. Moving on, similar to sample problem 4, sample problem 5 also deals with the weak base. In this problem, we are asked to compute for the hydroxide ion concentration and pH of a 0.01 molar sodium hypochlorite. Again, first step is to list down all the necessary givens and unknown. Again and again, I highlighted the concentration of the weak base, sodium hypochlorite. However, it can be seen that its corresponding Kb is not given. Instead, Ka was given. We will explain later what to do with Ka. Let's recall again the steps for a weak base. First is to write the expression for Kb. Next is to solve for the unknown concentration of species from the ice table. And then next and lastly is to compute for the POH using the following formula. Now that we have enumerated the steps, let's create the ice table. Again, the initial, change, and equilibrium concentrations are summarized in this table. Since Ka was given instead of Kb, we need to compute first for Kb using the following expression. Substituting the value of Ka will result to the following value of Kb. Kb now is computed to be 3.33 times 10 to the negative 7. Writing the expression for Kb will give us now, and then substituting the values in the ice table will result to the equation again is quadratic in nature and contains only one unknown. Again, you can easily solve this using your calculators. Solving for x will give us the value 5.75 times 10 to the negative 5 molar. Based on the ice table, this is also the hydroxide ion concentration. Substituting the hydroxide ion concentration to the formula for POH will give us the value 4.24. Solving for pH using the formula will give us 9.76. We have now completely solved sample problem number 5. Let us now discuss buffer solutions. Remember that when acids or base are added to buffer, or when acids or base are added to buffer solutions, they do not maintain the pH at a constant value. Instead, they only allow relatively small changes in pH. It is usually composed of the conjugate pairs, either a weak acid and its conjugate base, or a weak base and its conjugate acid. From this diagram, we can see how the buffer works. Focus your attention first on the top diagrams. The middle diagrams represent the buffer solutions. If a small amount of hydroxide is added to an equimolar solution of HF, for example, in this reaction, the HF reacts with the OH minus to make F minus and water. This is the reason why there is an observed decrease in HF concentration and an increase in F minus concentration. By contrast, if acid is added, F minus reacts to form HF and water. This is the reason why there is an observed increase in HF and a decrease in F minus concentration. Let us try to solve sample problem 6A. Calculating pH of buffer solutions. In this problem, we are asked to calculate the pH of a solution containing 0.4 molar formic acid and 1 molar sodium formate. Before we proceed with the solution, let us remember that buffers are composed of conjugate pairs of weak acids and bases. Thus, we can use the previously learned techniques in solving for the pH. Again, first step is to list down all the necessary givens and unknowns. I highlighted again the concentrations of the weak acid formic acid and its conjugate base formate. I also highlighted the Ka value as it is important in calculations of hydrogen ions for weak acids. Unlike weak acids or base, the concentration of the components are usually given in buffers, so no need to perform the ice table. Writing the expression for Ka and substituting the givens in the following expression will result to the value of X, which is also equal to the hydronium ion concentration, which is equal to 7.2 times 10 to the negative 5 molar. Plugging in the calculated H plus concentration to the formula for pH will yield the value 4.14. Sample problem 6A is now completely solved. Let's now move on to sample problem 6B. Calculating pH of buffer solutions. In this problem, we are asked to calculate the pH of a solution containing 0.2 molar ammonia and 0.3 molar ammonium chloride. It is similar to the previous problem that we have solved, so we can use the same steps we used earlier. Again, first step is to list down all the necessary givens and unknowns. I highlighted the concentrations of the weak acid ammonium and its conjugate base ammonia. I also highlighted the Ka value as it is important in calculations of hydrogen ions for weak acids. Unlike weak acids or bases, the concentration of the components are usually given in buffers, so no need to perform the ice table. Again, paulit-ulit tayo. Hindi na kailangan gawin ng ice table. Writing the expression for Ka and substituting the values for this expression will arrive at another quadratic equation. Sorry, it's not quadratic. We'll arrive at the following expression. Solving for x will yield, again, the concentration of the hydronium ion, which is equal to 8.55 times 10 to the negative 10 molar. Plugging in this calculated H plus concentration to the formula of pH will yield the value 9.07. Again, sample problem 6b is now completely solved. Remember that for buffer solutions, when strong acids or bases are added, it is safe to assume that all of the strong acid or base is consumed in the reaction. Mauubos lahat ng strong acid or base at ang matitira lang at equilibrium ay yung components ng buffer na again ay composed only of weak acids or weak base and their corresponding conjugates. Let's try solving sample problem 7a. Calculating the pH change after addition of acid or base to a buffer solution. In this problem, a strong acid HCl solution was added to a buffer containing 1 molar acetic acid and 1 molar sodium acetate. Again, the first step is to list down all the necessary givens and unknowns. I highlighted the concentrations of the weak acid acetic acid and its conjugate base acetate. I also highlighted the Ka as it is important in calculations of hydrogen ions for weak acids. I also highlighted the initial pH of the buffer solution to check if the change in pH upon addition of strong acid will indeed be small. Listing the initial and final concentration of the species, we have focusing our attention to the red boxes. It can be observed that the 0.01 mole of H plus converts an equivalent amount of acetate ion into acetic acid, resulting to 0.01 molar increase in the final concentration of acetic acid and a 0.01 molar decrease in the final concentration of the acetate. Writing the Ka expression and substituting the values, we will arrive at the pH equal to 4.73. When the final and initial pH is compared, again, the initial pH is 4.74. Upon addition of a strong acid, it became 4.73. It can be seen that there was almost no change in pH despite addition of a strong acid. The pH decreased only by a factor of 0.01. And this is the power of buffer solutions. Let's try solving sample problem 7b. Calculating the pH change after addition of acid or base to a buffer solution. In this problem, a strong base NaOH solution was added to a buffer containing 1 molar acetic acid and sodium acetate. Basically, the whole process is almost the same. Okay, instead of the 1 molar HCl, we added 1 molar NaOH in this problem. Listing again the initial and final concentration of this species, we have, focusing again our attention to the red boxes, it can be observed that this time, the 0.01 mole of OH would change the concentration of acetate ion to 1.01 molar and the concentration of the acetic acid to 0.99 molar. Writing the Ka expression and substituting the values, we will arrive at a pH equal to 4.75. When the final and initial pH values are compared, 4.74 yung initial, 4.75 yung ating final, it can be seen that there was almost no change again in pH despite the addition of the strong acid. The pH increased only by 0.01. Again, this is the power of buffer solutions. From the solutions we did with buffer solution, it can be observed that the steps are very similar. The series of steps are simplified further by the Henderson-Hasselbalch equation. It is an equation showing the relationship between a buffer's pH and the relative amounts of the buffer's conjugate weak acid and weak base. and it is represented by the following expression. pH is equal to pKa plus the logarithm of the ratio of the concentration of conjugate base over the concentration of the weak acid. You can always use this formula for buffer-related problems. Para mas makasigurado kayo na effective nga ito, you may want to try solving again the sample problems that we have solved earlier involving buffers or weak acids. Let us try solving sample problem 8, calculating the concentration of weak acid and conjugate base, given the pH of a buffer. In this problem, we are asked what concentration of the weak acid conjugate base pair should be used to prepare a cyanide-cyanate buffer with pH equal to 3.50 and pKa equal to 3.92. Because a buffer solution is involved, we will try to use the Henderson-Hasselbalch equation. First step is to list down all the necessary givens and unknown. Next is to recall the Henderson-Hasselbalch equation. Next is to plug in the givens. Then from here, we can see that we have two unknowns. However, we can treat these unknowns as a ratio, leading to multiple possible answers in the problem. Any solution, as long as the conjugate base weak acid ratio is 0.38, the pH of the solution will still be 3.50 or 3.5. For example, if conjugate base is 0.38 molar, then the weak acid must be 1 molar. Similarly, if the conjugate base is 0.76 molar, then the weak acid must be 2 molar. We have now completely solved sample problem 8. Let us now study some of the factors that can affect the buffering capacity of buffer solutions. Let us start with the effect of dilution on the buffer solution. From the figure, it can be seen that buffer solution has the greatest resistance to changes in pH when compared to unbuffered weak and strong acids. However, it can be seen that for dilute or low concentrations, the changes in pH become similar when compared to unbuffered weak and strong acids. Thus, it can be concluded based on this figure that dilution could decrease the buffering capacity of the buffer. Next, let us consider the common ion effect. It states that the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. Let us consider a solution of acetic acid. If acetate ion is added to the solution, Le Chatelier says that the equilibrium will shift to the left. If equilibrium will shift to the left, then less hydronium ions will be formed. Thus, resulting to a lesser degree of ionization. To better visualize this effect, let us try to solve sample problem 9. In this problem, we are asked to calculate the concentration of H plus ions in a 0.1 molar acetic acid solution. The common ion acetate's concentration was increased in the solution through the addition of sodium acetate. Again, the first step is to list down all the necessary givens and unknown. Since we are dealing with buffers, you can also use the Henderson-Hasselbalch equation to check. In this solution, we will use the Ka expression to solve for the H plus concentration. Substituting the values will result to H plus concentration of 1.2 times 10 to the negative 5 molar. Note that the concentration of H plus in a 0.1 molar solution of pure acetate or pure acetic acid is 1.3 times 10 to the negative 3 molar. Comparing the two values, it can be seen that the H plus concentration decreased when a common ion was introduced in the solution. In this example, the common ion was acetate. thus resulting to lower degree of ionization. I guess that is all for this video. Thank you for watching. I hope you have reached all the learning outcomes for acid-base equilibria. See you in our synchronous discussion. Bye!